Welcome. In this podcast, we're going to take a closer look at some of the standard approaches that we use in quantitation, calibration curves, and the method of standard addition. By the end of the podcast, you should be able to explain how to use these two common methods to quantitate analytes, and we're going to focus on UV-vis for right now, but you can apply it to other analytical techniques as well. Discern when it's most appropriate to use a calibration curve as versus when it's best to use standard addition. Define 6 standard analytical figures of merit used to evaluate analytical methods, and understand the purpose and the proper use of linear regression and the correlation coefficient in supporting your analysis using calibration curves. And so with that, let's get going. So what we're going to do first is we're going to focus on how do we actually generate the data or set up to do the analysis using a calibration curve. So the idea here is the first step is going to be to record a UV-vis for a standard sample of the analyte of interest and determine what's the ideal wavelength that you should use, what's lambda max, and what's the molar absorptivity for your analyte at that wavelength. Next, you're going to need to have some idea of what the concentration is for your analyte in your sample. And with this, then what you want to do is you want to set out to prepare a series of standard solutions containing your analyte that are in the approximate concentration range as you anticipate seeing in your unknowns. And ideally, if you really want to do this right, what you want to do is say, I think I might have as little as X micrograms of iron in water. I might see at most Y micrograms of iron in water. And then you want to set out to prepare your concentration range so it falls below and runs higher than the concentration range you anticipate seeing in your unknown. And once you've done that, you prepared that series of standard samples, then you want to basically record the absorbance for each of your standard samples at that lambda max. Now, if you plot the data, absorbance as a function of analyte concentration, you should anticipate obtaining a plot that's linear. After all, we're assuming Beer's law is obeyed. But remember, that's an assumption, and sometimes Beer's law is not obeyed. And so what we need to do is to generate a curve, a calibration curve, that shows to us and to others that over the concentration range of interest, we can indeed anticipate that there's a linear relationship between analyte concentration and absorbance. And so we're going to use a statistical technique known as linear regression because we're going to work with real samples. The standard samples are going to show real absorbance values. They're not perfectly going to fall along any linear line. And we'll plot them, and then what we need to do is figure out what's that best fit line that fits through our data points. We obtain this best fit line, we need to demonstrate that it really is linear to other people, and this is where statistics is going to come into play and the concept of using linear regression. But for right now, I want to back off of that, and I want to come back here, and I want to say it's important when you select an analytical technique to make sure that you understand your sample and analyte and you understand the underlying chemistry. And I say this because we're making assumptions even in the use of a calibration curve. And these assumptions include that our analyte is stable in solution, that it's not participating in any unwanted chemistry on the time scale of the measurements that we're making, that there really is only one material and that we're capturing it in the right form when we're measuring it at lambda max, and it is the analyte. And so if you are uncertain in terms of what's in your sample, you don't know a lot about your analyte, your sample of interest, this might not be a great approach to adopt. All right. So now let's talk for a bit about linear regression. From an analytical standpoint, I need to demonstrate to others that my system follows this linear relationship that lies at the base of my analysis, Spear's law. And that means I have to demonstrate statistically to others there really is a linear relationship between absorbance and concentration. And I want to mention that though we're focusing here on analysis of a UV-vis curve, we can apply the same concept to other analytical techniques as well. This could be, for example, electrochemistry, where we could be generating a calibration curve. So what are we actually doing when we say we're doing linear regression? Well, the name kind of tells you something about it, but we are minimizing the distance between any of our data points and the corresponding closest point on our best fit imaginary line. And so it's basically minimizing the distance between those points in that line. And if you think about it, some points will fall below and some points will fall above. So we'll get positive and negative deviations. And they could, if we just added them up in an effort to minimize the distance, these deviations, some would cancel out with others artificially. And so least squares is often given the name instead of linear regression, because what makes better sense to do is we minimize the square of the deviations from the best fit line. And so why are we minimizing the square is versus just taking those deviations? We square anything, it becomes positive, and in this way we're not going to artificially cancel out deviations. Now, the correlation coefficient is the parameter that we're going to use to demonstrate, or I should say, to evaluate the goodness of our regression. And correlation coefficients greater than 0.999 are generally considered to support a linear model. And so we're going to take a look at this parameter in the next couple slides. The correlation coefficient comes from recognition that if there is a linear relationship between two variables, x and y, then you really should be able to write two different equations that relate them. We usually write y equals mx plus b, and what we're really saying is that x is the independent variable and that y has this specific mathematical dependence on x, y equals mx plus b. But from a mathematical standpoint, we could also write the equation x equals some slope times y plus some intercept, or x equals m prime y plus b prime. Where basically we're now acting as if y is formally the independent variable and x is our dependent variable. So if that's true, we can really write these two equations, then I should be able to rewrite the first equation so that x is the dependent variable. And so that's what I'm showing you up top. If I do that using the equation y equals mx plus b as my basis, then I'll end up with x equals 1 over m times y minus b prime over m. And if this equation is going to be basically the same relationship as the second expression I wrote, or x equals m prime y plus b prime, then there is this very specific relationship between m and m prime. And that is that 1 over m, the slope in the x equals 1 over my minus b prime over m equation, has to be equal to m prime in that second equation. In other words, m prime has to equal 1 over m, and that means that 1 has to be equal to the product of m prime, or if we take the square root of both sides, 1 has to be equal to the square root of m prime, and I'm going to define that to be the correlation coefficient. And so experimentally, when I see r greater than 0.999, that value supports the proposition that there's a linear relationship between x and y in terms of variables. It is not proof, by the way. I want to make sure that I say that. It does not prove there's a linear relationship. Now, in lab this next week, you're going to use this approach, a calibration curve, to measure the concentration of iron in drinking water. You'll make a series of stock solutions containing known concentrations of iron. You'll measure their absorbance at lambda max for a chromophore. In this case, it'll be iron trisphenanthroline. And if you recall from our last podcast, this compound has a strong metal-to-ligand charge transfer transition, and that transition appears in the visible spectral range. When the metal is iron, it peaks about 508 nanometers, so that's the reason that wavelength is used for making the absorbance measurements. And you'll use linear regression performed either on your graphing calculator or with an Excel spreadsheet in order to determine the best fit line for your calibration curve and to ultimately determine the concentration of iron in your sample of drinking water. So now we talked about calibration curves as a method, and when you talk about using methods, people talk about choosing a right method, and part of what they're thinking about is a series of performance characteristics for analytical methods, and we call those analytical figures of merit. And they're extremely useful in helping analysts choose between a series of potentially useful methods, and they're also useful in helping analysts evaluate and optimize methods for use. And it should make sense to you that if an analytical method's purpose is fundamentally to quantitate an analyte, then from the get-go, the two most important terms that we're going to be concerned with are going to be the accuracy and the precision of your measurements. If I'm looking for the concentration of iron in drinking water and my method doesn't give me the right number, it's meaningless. And if I can't obtain a series of replicate analyses and I'm consistently getting that same number, it's also useless. Now, depending on what your research question is, I do want to point out that how accurately and how precisely you need to know the answer, well, again, that's related to your research question. So for some purposes, you may need to know your answers more accurately and precisely than for others, depending on the question. It may also be important, depending on your question, how low you're able to go and detect your analyte of interest. And this is the concept behind detection limit, or LOD, limit of detection. And as I've written here on the slide, it's basically 3 times the standard deviation for a blank sample. And the blank sample, of course, in principle, should not be showing a signal, because there really should not be any analyte in your standard sample that you're using for this curve. Now, let me explain sensitivity. Sensitivity I've written here is dy dx. Well, what is this? It's basically the slope of your calibration curve. And so in the case of UV-vis and the UV-vis calibration curve we just discussed, you're talking about the rate of change of absorbance as a function of analyte concentration. So the larger the slope is, what that's saying is the better I'm going to be able to discern small differences in analyte concentration. And again, depending on what my question is, that may be more important in some situations than it is in others. Dynamic range, again, fundamentally what this concept is saying is over how many decades of concentration is my calibration curve linear? Can I expect a linear relationship between absorbance and signal? Depending on your question, you may only need 1 or 2 decades. Depending on your question, you may need it over 5 or 6. So that's the concept of dynamic range. Now those are sort of, I'll say, the big 5: accuracy, precision, detection limit, sensitivity, and dynamic range. But there really is a 6th, I'll insist, and that's the practical analytical figure of merit. And under here, I'm sort of lumping together a number of other important considerations that really should not be ignored or neglected when you're considering choosing an analytical method. And these include things like the time it will take you to complete the analysis. For some questions, it may be important to get the results in a minute. In others, it might be okay if it took an hour. What's the cost of the analysis? Are there any special safety considerations that you need to think about? Maybe the place where you work isn't able to provide the resources so you can work with, say, radioactivity. We recently talked about our radioactive assays versus enzyme immunoassay in the case of the Discern paper. So, and lastly, you may also need to think a little bit about sample prep. Are there any special things that you need to do in order to make your sample suitable for the type of analysis that you're going to perform using that method? So those are the big six analytical figures of merit. Now, at this point, I'd like you to pause and consider for a moment the following question. Could you, or would you, choose to use a calibration curve in analyzing any of the following problems? And if not, why not? Can you make any generalizations here? And that's going to lead me to talk for a few minutes with you about the method of standard addition. And the method of standard addition, it's a really important method. It's a method that I should underscore is not just for UV-vis. All you need to know in order to use it is that the signal is directly proportional to the analyte concentration. And it's a very quick and easy method to adopt. It works best when you're dealing with problems where you have a complex sample matrix, the components of which you might not necessarily know, either in terms of composition or concentration. They may be variable in point of fact, say men, women, older people, younger people, characteristics like that. And some of the components of your sample matrix might even contribute to the background signal for the sample being analyzed. In circumstances like these, if we know there's a linear relationship between analyte concentration and signal strength, and we need to recognize this is an assumption, then we can use standard addition. In its simplest form, we basically make two measurements. We measure the signal for the unknown sample of interest, and then we make a second measurement where we spike at a very small volume of a concentrated solution of the analyte of interest into our sample. And generally, ideally, you would do this in the same cuvette, in the same sample cell where you made that original measurement of the absorbance for the unknown. And now you make that absorbance measurement for this mixture sample. Now, the reality is we often add a non-negligible volume of standard solution, and so please be careful, as you may need to take into account dilution of your standard and your unknown in your mixture sample. Now, quantitation is very quick and very easy. It's based on this linear relationship between absorbance and concentration. So absorbance of the unknown divided by concentration of the unknown is going to equal a constant, epsilon L. Epsilon, characteristic of that particular chromophore, L, the path length of the cuvette. And it's going to be, that product, epsilon L, will be the same, because it's the same analyte if we now create a mixture. And so that's going to be equal to the absorbance for that mixture divided by the concentration of the analyte in that mixture. So that term is going to have two components: the concentration of the analyte due to the standard and the concentration of the analyte from the unknown. And You can simply call the concentration of the unknown X, plug in your numbers, and solve. Very nice method. And again, I said it before, I'm going to say it one more time. Just like calibration curve, standard addition is a technique that you can use with a wide range of spectroscopic and electrochemical methods, not just UV-vis. So let's actually do that and expand your mind, and we'll try a problem based on using electrochemistry. And you don't have to know any electrochemistry to solve this problem. So here we're measuring current for zinc in seawater. And we're going to use standard addition. And so we measure the current for a set sample of seawater, and we find what that current is. And then we're going to add to it purposefully 1 milliliter of a 0.2 millimolar zinc standard, and we're going to re-record the current. And now we find it's increased because we have more zinc in there. It's 0.32 microamps. And then this is the all-important piece. You're told, given there's a linear relationship between the concentration of zinc and the diffusion current, calculate the zinc concentration. And so that's what we're going to do now. And for those of you who'd like to try this problem by yourself, I'm giving you the answer up front. You can simply pause the podcast here, work through the problem, check your answer. And for those who would like to work through the problem with me, we'll simply do that now on a blank slide. All right. So let's set everything up. So we have two measurements. First we made the, let me set it up as a general equation first. We have the current for our unknown, and we have the concentration of zinc for our unknown. And that's simply a constant. It's equal to a constant. Oops. And that's going to be equal to the current for my mixture divided by the concentration of zinc for my mixture. And so now I'm going to set out to plug in first the left-hand side over here. So I had 25 milliliter sample of seawater with zinc in it, and the current was 0.14 microamps. So 0.14 microamps is to, and I'm just going to leave it as it is, concentration of zinc. And then it has to be equal to, on the right, the current for my mixture. And I'm told that was 0.32 microamps. Oops. And as you can see, I have microamps on the left, I have microamps on the right. That's why I didn't bother to change that into amps. They're both going to cancel out. And now I have to evaluate in the denominator the concentration of zinc in the sample. So as I said before, there's two components to it. I need to figure out how much zinc there is being contributed to this mixture sample from the standard. So this is a dilution problem. So it's going to be, I have 1 milliliter of 2 times 10 to the minus 4 molar zinc. And that's going to be in a total volume of 26 milliliters. And I think you can see I have units of milliliter on top and bottom, so that's why I didn't change to liters there. And I have one more component. That was my standard. I have my unknown zinc sample. Well, I had 25 milliliters of it. Its concentration is zinc, and it's been diluted to 26 mils. So milliliters cancels out, microamps cancels out. Everything looks really nice, and you can see the units for my concentration are going to end up being molarity. So now what I want to do is to rearrange and solve here. So I'm going to multiply both sides by the concentration of zinc. And so I will have 0.32 times the concentration of zinc. Oops. Concentration concentration of zinc equals 0.14 times this little bit of a mess, and let me clean this part of it up. That's going to be 1 times 2 times 10 to the minus 4 divided by, that's going to be 7.69 times 10 to the minus 6 plus 0.9615 times the concentration of zinc. And so let me divide both sides by 0.14. And let me evaluate that. So that's going to be 2.2857 times the concentration of zinc equals 7.69 times 10 to the minus 6 plus 0.9615 times the concentration of zinc. And I'll subtract the 0.9615 from both sides. And so that will give me 1.3242 times the concentration of zinc equals 7.69 times 10 to the minus 6. And if I divide both sides by 1.3242, that's going to give me the concentration of zinc equals 5.8 times 10 to the minus 6 molar, or 5.8 micromolar for my zinc concentration. And we're done. All right, so that will bring this particular podcast to a close.